carry look ahead adder, carry skip adder, carry select adder, and lastly the summary. So we know that floating point operation takes more time as they involve integer operation too. Therefore, if we increase the speed of integer operation, that is specifically addition, then floating point operation speed automatically increases. We know that addition is the main operation in all the processors performed by the logic blocks called as adders. Adders are nothing but the combinational logic blocks, that is, they do not include the clock signal. The adders are not only required in performing the addition operation, but also in other operations like incrementing the program counter, and whenever we have branch instruction, adders are required to calculate the next address. So these are some of the operations where adders are required. So there are many adders available to perform the addition operation. The basic adder is ripple carry adder, which is obsolete nowadays. Other adders are like carry look ahead adder, carry skip adder, carry select adder, which are faster than the ripple carry adder. In the next slide, we will see three adders, that is CLA or carry look ahead adder, carry skip adder, and carry select adder. So we know that the sum, that is the ith sum, can be given by the equation that is given here. It depends upon the inputs A and B, and C is the carry bit. But the problem here is circuit has to wait for CI to operate. That is, it has to wait for carry to ripple through all the blocks to calculate the sum. Therefore, we need to generate CI from AI and BI, that is only input directly. It can be done by using the carry generate and carry propagate. Carry generate can be given by G, carry propagate can be given by P. Now, CI can be given by the equation that is given here, that is GI minus 1 plus PI minus 1 multiplied with CI minus 1, where GI minus 1 is equal to AI minus 1 into BI minus 1, and PI minus 1 equation is also given here. So substituting the values of GI minus 1 and PI minus 1 in the equation CI, it mostly depends upon the inputs A and B only. So here we will see what is meant by carry generate and carry propagate. So if in the equation CI, that is equal to GI minus 1 plus PI minus 1 multiplied with CI minus 1, if GI minus 1 is true, that is, if GI minus 1 is 1, then CI will be automatically 1 because there is OR operation happening there. And CI is high in another condition, that is when PI minus 1 is equal to 1 and CI minus 1 is equal to 1. These are the two conditions where CI will be equal to 1. Now, by replacing the value of Ci minus 1 in equation Ci, that is, Ci minus 1 will be equal to Gi minus 2 plus Pi minus 2 multiplied with Ci minus 2. And then again by replacing the equation of Ci minus 2, we will get last equation, that is the length equation that is shown here. So here we can see that in that equation, Ci, that is carry, only depends upon P and G, that is carry propagate and carry generate, which are obtained by using inputs A and B. And here in the last term, we can see C naught, that is nothing but the input carry. Therefore, we can say that Ci depends on only input carry and P and G values. So here, instead of using the logic of carry ripple adder, the blocks, that is the carry out, Block will not wait for the carry to ripple through all the blocks. It can be calculated directly from the equation that is shown here. So here we can see the CLA logic diagram. The disadvantage of this architecture is in the OR gate. We can see the OR gate is present here, and the AND gate, that is the rightmost AND gate. They require n plus 1 fan in for n bits. Here we can see that many number of inputs, that is if n bit adder is there, then we require n plus 1 inputs, that is the fan in. So this is the main disadvantage of carry look ahead adder, and another disadvantage is that it requires long wires. Thus, we can improvise this architecture. We will see how we can improvise this architecture. We know that C1 is equal to G0 plus C0 into P0. That is, C1 is high if the first block of carry generate is high, or first block of carry propagate and carry in are high. So similarly, we can write the equation for C2 as well. C2 is given by G01 plus P01 into C0. That is, C2 is high if the first two blocks of carry, C2 is high if carry is generated from the first two blocks, that is block 1 and block 2. Else, it is high if carry is propagated from first two blocks, block 1 and block 2, and if C0 is high. So this is the equation given for C2 and so on, where G01 and P01 are given by the equation G1 plus P1 G0, and P01 is given by the equation P1 into P0. Therefore, we can generalize all the equations. That is, we can generalize the equation for the carry bit, the carry generate and carry propagate that we can see here. So, here the carry look ahead adder can be divided into two parts. One part will generate only G and P values, and another part will generate carry values. That is, using the values of G and P, carry can be generated by using the values of G, P and C0, that is the C in given by the user. So this is the first part, that is, this architecture is used to generate the values of G and P. So G and P, we can see that in the first block, that is given by 111, the the G and P are generated from the input values A and B, and so on. So this is the 8-bit adder. So therefore, 8G and 8P values have to be generated. So here we can see the output where 8G values from G0 to G7 and 8P values from P0 to P7 can be generated. So this is the first part of carry look ahead adder. And this is the second part of carry look ahead adder, where the carry is generated from the values of G and P. Here we can see that C0 is only the input carry that is propagated. Other all carries be generated from the values of G and P. Therefore, we can say that this carry out, that is C out, does not depend on the ripple, that is the rippled carry from all the blocks. It only depends upon the input and the input carry, that is C in. And this is the complete carry look ahead adder, that is combining the both architecture that we have seen before, that is the first part and the second part of the carry look ahead adder. By combining the architecture which generates P and G values and carry values, we will get the complete carry look ahead adder tree as shown here. So this is all about carry look ahead adder. Next we will see carry skip adder. So from the carry look ahead adder, we have got the equations for P and G. So if we are using the 4-bit adder, then the P equation will be equal to P0, P1, P2, P3, and G0 3 equation will be equal to the given equation, which is a bit lengthy compared to the P equation. So we can say that computing G is much more complex than computing P value. Computing P value is very easy as we just need to add the P values. So in carry skip adder, we only calculate the P values. We just ignore the G values. We can see that here in the architecture, we can see that each block, here we can see each block consists of 4-bit adder. That is, it consists of 4 1-bit adders. C4, that is, we can see here the output, that is the carry output of the first block. It does not depend upon the C0. If any one of the block in the first block generates a carry, then C4 will be equal to high. That is, assume that A2 and B2 are 1 1. Therefore, the carry is generated from that block. Therefore, automatically C4 will be high, and C4 will be multiplied with P4 7. That is the P value, and the output is given to the next adder, that is the OR gate that we can see here. So the operation continues. Therefore, all the blocks operate simultaneously, and they do not wait for the C0 to propagate through each block. This is how carry skip adders operate. Next we will see carry select adder. Here, 2 additions are performed in parallel. One addition is done by assuming carry in is equal to 0, and one addition is performed by assuming carry in is equal to 1, that we can see here. When carry in is given by the user and the carry is propagated, then the sum or the correct sum is selected and given as the output. Here we can see that 8-bit adder is divided into 4 4-bit adders. That we can see here. The first 4 bits are performed as it is, and the carry is given to the next block. For the 4-bit block, for the 4-bit, that is the last 4-bit adder, it is divided into 2 parts. Therefore, the additions are performed simultaneously, and depending upon the C4, multiplexers are used here. So, C4 is nothing but the select line for the multiplexer. If C4 is equal to 0, then the first sum, that is the sum from the first block is selected. If C4 is equal to 1, then sum from the second block is selected. Therefore, we can say that 2 additions are performed in parallel. Therefore, it consumes less time compared to other adders. This is about the carry select adder. Next, we will see the summary. For n-bit addition, ripple carry requires n time units and n adders, and CLA uses log n time and n log n space. Here we can see that carry skip and carry select use less time as well as same space as that of the ripple carry adder. So if we want to improve the time in the addition, then we have to go for carry skip and carry select adder. If the constraint is the area or space, then we can go for CLA. So this is about the adders. Thank you.
Okay, that's good. Next one can continue. Meanwhile, just whenever you find time, this is whatever theoretical background you have got now. So why we are combining 4-bit triple carry adder? Why not 8 till 8 bits? So with whatever the scaling you have obtained, say time is n or the linearly scales or the space is also n. So then there is a
Okay.
combining of bits with respect to 4 bits. So if you can just make it a habit. So synthesis is something with respect to Xilinx ASC or cadence. Make sure that you do it by structural coding, because most often the optimization will kill your intentions. So there are optimization algorithms running into your tools, so which will make sure that the most optimized circuit. Most oftenly, so optimization goals will be defined. So speed or area, depending upon that, a particular architecture is chosen. So force it to generate the circuit you want to generate, and then compare with respect to timings and space, whatever it has consumed, and then you have a fair, realistic comparisons. So whenever you, I mean to say, with whatever the technology you are using, ಸೊ ನೀವು ಸ್ಪಾಟನ್ ಟು ಯೂಸ್ ಮಾಡ್ತಿರೋ ಅಥವಾ ವರ್ಟೆಕ್ಸ್ ಯೂಸ್ ಮಾಡ್ತಿರೋ ಅದರಲ್ಲೇ ಒಂದು 4 ಬಿಟ್ಟು ಅಥವಾ 6 ಬಿಟ್ಟು, ಹಾಗೆ ಇಟ್ ಡಿಪೆಂಡ್ಸ್ ಬಿಕಾಸ್ ಇಟ್ಸ್ ನಾಟ್ ಡೈರೆಕ್ಟ್. It is generating from the technology library, and hence there can be variation in the numbers of the figures as such, but you will get a fair idea. Okay, so next one, please continue.
Thank you.
Good morning, sir.
Yes, good morning, go on.
My topic is on introduction basic techniques of integer arithmetic. So we will study table of contents, that is introduction basic technique of integer arithmetic, ripple carry adders consisting of n full adders, radix 2 multiplication and division, sign numbers, sign numbers and system issues. So first we will study the introduction. So the computer arithmetic is sometimes viewed as a specialized part of CPU design. It is a very important part. So
uh, Hello, so you are not audible.
now we will study the basic techniques of integer arithmetic. In this study about the ripple carry addition, radix 2 multiplication and division, and uh, s- um some signed numbers and system issues. So here first is the ripple carry adder. So ripple carry adder is nothing but the adders are usually implemented by combining multiple copies of simple components. So the natural components for addition are half adders and full adders. This is we have the half adder and full adder. So the half adder takes 2 bits, that is A and B, as an input, and
Hello,
produces a sum bit.
you can hide that sharing tab.
Hello.
So please hide the sharing tab, it's on
Yes,
your
sir.
instruction.
Yes. Yes, sir.
Yeah,
I've
okay.
hidden, sir.
Okay, okay. Yes, continue.
I'll start, sir.
Continue.
So here we have the yes, sir. So the half adder takes 2 bits, that is A and B, as an input and produces a sum, that is S, and that is sum and carry bits. So here we have S is equal to A plus B mod 2, and C out is A plus B by 2, where we have shown some symbol that is nothing but a floral function. so the full adder, that is so this is the ripple carry adder consisting of n full adder. So here it says that when we are so the principal problem in constructing an adder for n-bit numbers out of the smaller pieces is propagating the carriers from one piece to the next. So the most obvious way to solve this is with ripple carry adder consisting of n full adders, as we have shown in the figure. So here the inputs of the adders are that we are taking the inputs, that is a n minus 1 to a naught, that is the input, and b n minus 1 to bn minus 1 to b naught, that those also are the inputs. And here uh, output, here ci plus 1 is nothing but the output of the ith adder is fed into the ci plus 1. So here the input of the next adder, that is I 1 plus I plus 1 adder with the lower order carry in, that is C out, set to 0. Since the lower order carry in is y to 0, the low order adder could be the half adder. Later, however, we will see this setting the low order carry in bit to the 1 is useful for the performing subtraction. So here we can see that this ripple carry adder, which is consisting n full adder, says that the carry out of one full adder is connected to the carry in of the adder for the next most significant bit. So the carriers ripple from the least significant bit, that is from right to left. So next is the radix to multiplication and division. So here the simplest multiplier computes the products of two unsigned numbers, that is one bit at a time. As we can see here, that is here in this figure we can see the number to be, here we are multiplying the number, that is a n minus 1 a n minus 2 to a naught, and b n minus 1 b n minus 1 comma b n minus 2 to b naught, and they are placed in the register. Here a and register are nothing but a and b are the registers. P is the initial value, where we are giving the initial value, that is 0. So for this we are doing the first we will do the multiplication, and then the how then we are going to divide. So first is the multiply steps. So here in the least significant bit, a is set to 0, then register b containing bn minus 1 bn minus 2 to b naught, where uh, is added to p, where p otherwise means p, we can p is nothing but 0 bit to the end of the 0 is added to p. So the sum is placed back into the p. Now here register p and a are shifted right, means p and a are shifted to right with the carry out of the sum being moved into the high order bit of p. So the low order bit of the p being moved into a register a, and the rightmost bit of a with which is not used to set of the algorithm, that is being shifted to shifted out. So here figure b, that is figure b is showing so here each multiplication steps consisting of adding the contents of p to either b or 0, where it depending on the low order bit. So low order bit a, here it is depending on the low order, that is low order bit, that is 0, that is a, sorry, replacing p with the sum and the shifting both p and a. One be right. Each division step involves first shifting p and a, one bit shift, subtracting b from p, and if the difference is non-negative, putting it to p. If the difference is non-negative, the low order bit of a is set to 1. Now we will see the divisions divided step. Here in divided step we have four steps are involved in the division divided step, where shifting the register pair, that is p comma a, to one bit left, then subtract the content of the register b. B is nothing but bn minus 1 bn minus 2 to b naught from the register p, putting the result back into the p. If the result of step 2, that is 2, is negative, set the low order bit of A to 0, otherwise to 1. Fourth step, that is, if the result of step 2 is negative, restore the old value of P by adding the contents of register B back to P. So after repeating this process n times, the A register will continue the quotient and the P register will continue contain the remainder. So this algorithm is the binary version uh, of this method. So here now we have the divided steps, that is non-restoring is nothing but if P is negative, then it is the non-restoring uh, process. Divided divide steps, that is when I minus A, I to A is shift is a shift register pair, that is P comma A, one bit to left. Then to add the contents of the register B to A. Then else, if that else the shift register pair P comma A, one bit left, then subtract the contents of the register B from P. If P is negative, set the low order bit of the A to 0, otherwise set it to 1. Next is the signed numbers. So there are four methods commonly used to represent signed n-bit numbers, that is sign magnitude, two's complement, one's complement, and biased. So in the sign magnitude system, the high order bit is the sign bit and the low order bit, that is n minus 1 bits, are the magnitude of the number. So in this complement system, a number and its negative add up to 2 raised to n. So in one's complement, the negative of a number is obtained by complementing each bit. So in each of these three systems, non-negative numbers are represented in the usual way. So in a bias system, non-negative numbers do not have their usual representation. So all numbers are repeated by first adding them to the bias and then encoding the sum on as an ordinary unsigned numbers. So thus a negative number k can be encoded as long as k plus bias that is greater than or equal to 0. A typical value for a bias is 2 raised to n minus 1. So here they have taken some, that is to add 5 plus minus 2, for example, taking adding 0101 to 2 bit and 1110 of 2 bits, which obtains, which we to obtain, that is 00112, which resulting in the current value of 3. So in initial content, so there are three approaches, that is set a bit on a overflow, trap on overflow, or do nothing on overflow. In the last case, software has to check whether or not an overflow occurred. So the most convenient solution for the programmer is to have an enable bit. So the first is to have an single cycle multiple steps instructions. So this might do one step of the Booth algorithm. So the second approach is to do integer multiplication in the floating point unit and have it to be a part of the floating instruction set. So here taking an example, that is as example, the original SPARC has a multiple steps instruction but no divide step instruction, while this MIPS R3000 has an autonomous unit that does multiplication and division. So in graphs, when converting from one coordinate system to another, there is no glitch near zero. For example, to convert from a value x expressed in a system that uses 100 dots per inch to value y on bit mapped display with 70 dots per inch. So the formula, that is y is equal to 70 into x dividing 100 maps 1 or 2 x coordinates into each y coordinate. But if division were defined as in a pascals to be x by y rounded to 0, then 0 would have three different points, that is minus 1 comma 0 comma 1 mapped into it. Now coming to the system issues. So in issues, sorry. Thank you, sir.
Okay, just one observation or one suggestion. Don't follow me as my classes where I am just showcasing PDF and entire textual content. So whenever you are presenting, make sure that there are key points and appropriate equations, and your pronunciation and slide doesn't go in hand. You are saying 2 raised to n and it is showcasing 2n and 2n minus 1 kind of stuff. So that creates ambiguity for yourself. So I feel if you are representing number ranges, then it is 2 raised to n. Otherwise, just summation, I feel it is 2n kind of stuff. So clear that, and most oftenly keywords, equations, and
Not able to hear, sir.
so I hope my mic is on. Yes, it's vibrating. So only she is not able to hear, or everybody is?
So we are able to hear, sir.
Able
Oh,
to hear, sir.
okay. Just general suggestions. You convey her later part. So
Yeah, I'm able to hear now, sir.
fine. So whenever you are preparing slides, just make sure that textual content is as low as possible, not more than 4 tabs or bullets per slide. So slides are meant to glance. Uh, so it is general suggestion for any presentations you are carrying out. So I had this time and I underlined it and I showcased it. So I'm sorry for that particular part, how I took class, but that is not the right way. So right way is basically slide should be as minimal textual content. So go with the graphics, equations, and flowchart, whatever you can put onto the slides, so that major focus is onto the presenter rather than the slides. Slides just you should take 1 or 2 seconds to glance. That's how it should be. Right? A general guideline. So next, anybody is ready? You can just go
Okay, sir. Thank you, sir.
on.
Sir, I'm doing visualization.
Yes, go on.
Good morning, sir.
Good morning.
Yes.
ಸೊ ಇಬ್ರು ಒಂದರಲ್ಲಿದ್ರಿ ಆಯ್ತು.
Good morning, everyone. It's Vijay Lakshmi and my presentation on floating point addition and division and reminder. As we know that in normal addition we'll take two numbers and we'll add. In when it comes to the floating point addition and division, there is a different way to add the numbers and divide the numbers, and we are going to discuss about that. And the content is floating point addition, speeding up the addition, denormalize numbers, division and reminder, floating point reminder. First, we going for the floating point addition. Typically, floating point operation takes two inputs, p bits and precision return to a p bit result. The ideal algorithm would compute by first performing the operation exactly and then rounding the result p bits. The multiplication algorithm presented in the previous section, it's in Anupama's slide, she had told about that. It does not need actual perform the ideal algorithm. For addition fact, there better way to proceed. To see this, consider some, we'll take some examples. First, take the binary 6-bit binary number, which is 1.100112 and 1.10012 to the power of minus 5. Once they are shifted, they have a same exponent. The exponent is shifted. So when we have 2 to the power of 5, we can write it as 0.00001. It has shifted to 5 places. Hence, we can get 4 zeros there. And after getting these numbers, we have to add the numbers. When we add the binary numbers, we'll get the answer 1.10100.
and discard the extra bits which we have to discard the other bits which are not in the addition. The rest of this section detailed discussion of the floating point algorithm. Let A1 A2 be the two numbers to be added. Notation EI SI used for the exponent significant in the addends AI. This means the floating point inputs have taken unpacked and it is SI explicit leading to the bit. To add A1 and A2, we have 8 steps to perform, which are nothing but addition algorithm in the floating point numbers. First step is if E1 is less than exponent is less than E2, swap the operands. This ensures that difference of the exponent satisfied. D is equal to E1 minus E2 is greater than 0. Tentatively set the exponent of the value of result to the E1. If sign of A1 and A2 are different, multiply S2 by 2's complement and place S2 P bit register and shift it to a D is equal to E1 minus E2 place to right. From shifted bit out, set G to the most significant bit, set R to the next most significant bit, and set the sticky or the rest. Compute the preliminary signed S is equal to S1 plus S2 by adding S1 to the P bit register contain S2. The most significant bit of S is 1, there is no carry out, then S is negative. Replace S with the 2's complement. This can be happen when D is equal to 0. Shift S as follows. It signs the A1 and A2 are same. There was a carry out in step 4. The shift S is right by ones, filling the high order position with a 1. Otherwise, shift left until the normalized. When left shift on the first shift, fill the low order position with a G bit. After that, shift zeros. Adjust the exponent of the result accordingly. Adjust R and S. If S is shifted right, as we given in the step Y, the R is equal to low bit of the S before shifting, and S is equal to G or R or S. It is S is nothing but G or S or S. There is a no shift. Set R is equal to G, S is equal to R or S. There is was a single left shift does not change R and S. If there were the more left shifts, R is equal to 0 and S is equal to 0. Seventh step, the round S figure, namely the table entry non-empty, add the 1 to the low order bit of the S. Eighth step is compute the sign of the result A1 and A2 and same sign. We'll see one problem here. These are the some of the refers to the swapping of the operand in the step 1. Example, we have taken the one example here. First step, we are giving S1 is less than S2. So we are swapping to the D is equal to 2. Here exponent is 0. Sign the both operands negative. Don't negative the S2. We have a both are positive, so we don't have to negate the S2 operation. Shift the S2 right by 2, giving that 2 is equal to 0.10, 0.010, G is equal to 0, R is equal to 1, and S is equal to 0. Then add the numbers. Then we'll get this answer. S is equal to 0.001 with the carry out. The carry out, so shift the S right, S is equal to 100. As we know that exponent is equal to exponent plus 1, so exp is equal to 1. R is equal to low order bit of the sum, which is 1, SVRBS, which is 0V010 is equal to 1. R and S true. So figure J11 says round up the S is equal to S plus 1 and S is equal to 1.00. Both signs are negative, so sign of the result negative. Final answer is minus S 2 exponent of 1.0012 and 21. Speeding up the addition. There are several techniques used to speed up the addition. One of is pipelining. The putting all together section examples the how commercial chips are pipelined additionally. Let's estimate how long it takes to perform the algorithm. As we know that step 2 require a addition, step 4 requires one or two additions, step 7 may require addition, but it takes a t times you need to perform p bit. It takes more amount of time. We when we go through all 8 steps, it takes the more amount of time to add a single number, but we have to get the answer within a fraction of second. So speeding of the addition, we are using some of the techniques in this. The first technique is used pipelining. We put all together and we'll add and get the answer, which will be reducing the time as compared to the previous algorithm. And another method we are using is two additions parallelly. When we perform the addition parallelly, we'll get the answer simultaneously, or we can reduce the time. We can reduce the time when we add parallelly. We can add the two numbers. So we need to explain how it reduce latency from 3t to t. Denormalized numbers. Unlike multiplication for addition, very little changes in the prediction and description one of the inputs denormal numbers. There must be, unlike multiplication for addition, very little changes in preceding description of one of the inputs that denormal numbers. There must be a test to see exponent is filled is 0. If it is, then when we unpacking the significant, there will be no b leading to the 1. By setting the biased exponent to 1 when unpacking the denormal, the algorithm works unchanged. To deal the denormalized output, we are using the step 5 in the algorithm, which has to modify it very slightly, where it tells a shift s is until it is normalized or until exponent becomes e minimum. The exponent is e minimum after rounding the higher order bit to s1, then result normalized number should be packed in the unusual way. It We have to change the exponent to 1. If the other hand the higher order bit is 0, the result is denormal. If the higher order bit is 0, then result is denormal. When the result is unpacked, the exponent must be set to the section set to 0. Incidentally, detecting the overflow is very easy. It can happen in the step 5 involves right shift of the biased exponent as shown. And division. What actually division is? When we dividing the floating point is very different. When we divide the two numbers in the normal numbers, when we divide the steps used here is different from there. And how we are going to divide the numbers? We have only three steps. There are a division algorithm we can say. First, compute the exponent of the result by subtracting the exponent. Here we are taking the S1 and S2 and we are dividing S1 by S2. When we divide the S1 by S2, the exponent has to be subtracted. Here we are giving S1 into 2 e to the power of 1 divided by S2 into e to the power of 2 is equal to S1 by S2 into 2 e to the power of 1 minus e to the power of 2. When we go for the division, the exponent has to be subtracted. Next, first step is compute the exponent result by subtracting the exponent. First, we have to subtract the exponent, then divide the magnetia and decide the sign of the result. Then we have to go for magnetia. Magnetia is nothing but here we have 2 e to the power of 2. 2 is the S1 into 2 e to the power of 1. S1 is the magnetia and at it is 2 e to the power of 1. E to the power of 1 is the exponent. Divide the magnetia and decide the sign of the result.
Please note
Normalize
it's
and
mantissa.
round the necessary value if it is
There is no
necessary.
magnet
Then
after.
third step is normalize the value, round up the values. Sir,
Mantissa ಅಂತ ಹೇಳ್ತಾರೆ ಸೇ ಸೈನ್ ಬಿಟ್
sir,
exponent and then mantissa.
man,
You please note the spelling.
mantissa. Okay. Mantissa.
Huh.
uh, and first we have to divide minus the exponent, then we have to divide the mantissa, and then we have to add those numbers and we'll get the answer of the division. Floating point number. For non-iterative integers, integer division as reminder satisfy a is equal to a div b plus it is the formula we have to get the reminder a div b plus a reminder of b. The floating point reminder x into x reminder y can be similarly defined as x is equal to integer x by y into y plus x reminder y. How should x by y converted into integer? IEEE reminder function uses the round to 11 even rule. That is, pick n is equal to integer x by y so that x by y minus n is less than or equal to 1 by 2. If two different and satisfy the relation, pick even one. Then reminder is defined to be x minus yn, unlike integer when 0 is less than or equal to a. Reminder b is less than or equal to b. Floating point numbers like x mod of x reminder y is less than or equal to y by 2. Although this defines the reminder preciously, it is not a practical operation defined because we can use a single precision could have large of 2127 by 2 minus 126, which is nothing but a 2253 approximately of 10 1076.
What is it? So do you have any idea
There is
what
a
is this?
natural way to compute reminder if a direct division algorithm is used processed as you were computing exponent. Sir,
Yes, continue.
there is a natural way to compute a reminder if direct division algorithm is used processed as if we are computing the x by y. If s1 is equal to 2 e to the power of 1 and y is equal to s2 e to the power of e2, the divider in figure load the s1 to p and s2 to b. After e1 minus e2 division steps, the p register will hold the number of r in the from x of y and satisfying 0 is less than or equal to r less than y. Since IEEE reminder satisfies mod of reminder is less than or equal to y by 2, reminder is equal to either to r or r minus y. It is only necessary to keep the track of the last coefficient bit produced, which is needed to resolve half cases. Unfortunately, E1 minus E2 can be a lot of steps, and floating point units typically have maximum amount of time they are allowed to spend in the instruction. REM can be used for computing trigonometric functions. To satisfy things, imagine you were working based on 10 with the 5 significant figures and consider computing sin x. Suppose that x is equal to 7, then we can reduce by pi is equal to 3.1416 and compute sin 7. Sin 7 minus 2 in 2 pi 2 into 3.146, which is nothing but sin 0.1768 instead. But suppose we want to compute sine 2.0 into 1.5, then multiply 2 into 105 divided by pi value 3.1416, then we'll get the answer, which is in our 5 place of the system, comes out of the 63622. Since multiplying 3.1416 times 63622 gives 20000.5392, which rounds up to 2000 into 105. Reduction reduces 2 into 1.520, which is not even close to the being correct. Thank you.
Okay, I'm not much convinced with respect to whatever the trigonometric remainder or whenever you represent the numbers with respect to floating points. So already it is covered that you are more worried about quotient rather than the remainder. Whenever you follow up an integer arithmetic, yes, there is a scope for reminder, because something cannot be divided by the divisor and that remains as a reminder. Floating point representation automatically covers that. Maybe one application showcase trigonometric that was not much convincing as such. Make sure that you go through thoroughly that for that. Okay, next, anybody wants to continue? Continue.
Okay.
Good afternoon, sir, and good afternoon, my friends. My name is Musral. Today, I am going to present a advanced computer architecture seminar. So, my title name is floating point and floating point multiplications. These are the some contents which I am going to discuss in a further slides. That is a floating point and related to that example, floating point multiplication and related to that one example. So first is a floating point. In many applications require a number that cannot integer. There are a number of ways that non-integer can be represented. One is to use a fixed pointer, that is use integer arithmetic and simply imagine the binary point somewhere other than just to the right of the least significant digit. Adding to such a number can be done with the integer addition, whereas multiplication requires some extra shifting. Other representation that have been involved storing the algorithm of a number and doing multiplication by adding the algorithms or using a pair of integer. In this system, a computer word is divided into two parts, as an exponent and a significant. As an example, an exponent of -3 and a significant of 1.5 may be represented the number as 1.5 into 2 to the power of -3, which is given as 0.1875. So floating point representation. This figure shows the floating point representations where this 4.2 is represented as a mantissa and this 10 is represented as a base and 8 is represented as a exponent. So we have some IEEE standards to follow the floating pointer. That is structure of floating point number and it defines main four sizes of floating point number, that is 16, 32, 64 and 128-bit memory. Sometimes referred to as a half, single, double and a quadruple precision. IEEE arithmetic differs from many previous arithmetic in the following major ways. That is, um,
Sir, Musrat's screen is not visible.
yeah,
No, it is visible for me.
Screen is not visible.
ಅವ್ರಿಗೇನು ಸ್ಕ್ರೀನ್ ವಿಸಿಬಲ್ ಆಗ್ತಿಲ್ಲ ಅಂತ. So for me it's visible. You can
okay,
just
sir.
close it and share it again.
Okay, sir. Now is it visible?
For me it's visible.
Ah, visible.
Vijayalakshmi?
Visible.
Okay.
Okay.
Yes,
Uh,
yes,
I
it's visible.
okay.
Okay, you can continue.
IEEE arithmetic differs from many previous arithmetic in the following major ways. First one is when rounding a halfway result to the nearest floating point number. It picks the one that is even number. And second one is it includes the special value that is a negative number, infinity and minus infinity number. It uses a denormal number to represent the result of computations whose values is less than 1.0 to uh, 2 e minimum. It rounds to the fourth one is it rounds to nearest by default, but it also has three other rounding modes. Fifth one is it has sophisticated facilities for handling exceptions. Note that when operating on two floating point number, the result is usually a number that cannot be exactly represented as another floating point number. For example, in a floating point system using a base 10 and a 2 significant digit as a 6.1 into zero point 0.5, which gives the values of 3.05. This needs to be rounded to two digits. It should be rounded to 3.0 or a 3.1. But in the IEEE standards, such halfway cases are rounded to the number whose low order digit is even number. That is 3.05 rounds to the 3.0, not to the 3.1. The standard actually has four rounding modes. Special values and denormals. Special values in the standard are denormal numbers. In many floating point systems, if E minimum if E minimum is the smallest exponent, a number less than 1.0 to 2 E minimum cannot be represented, and a floating point operation that results in a number less than this is simple, flushed to zero. In the IEEE standard, on the other hand, number less than 1.0 to 2e minimum are represented using a significant less than 1. This is called a gradual underflow. Representation of a floating point number. Here we are used a 32-bit floating point representations. From this table, first from left side, one starting first bit is represented as a sign number. If it is 0, then it shows that the number is a positive number. If it is a 1, then it shows the number will be a negative number. And this 8 bit is represented as an exponent number, and this 23 bit will be represented as a mantissa number. By adding this 3 bit 23 plus 8 plus 1, we will get it as a 32 bit. For example, we want to format of a number to be in m into b to the power of e. M is where m is a mantissa, b is a base, and e is a exponent number. We want the mantissa to be single decimal digit. So, for example, this is a one example 3450, which is here is a we have a 1 point. We are shifted left to the 3 digit. So that's why we are multiplied by the 10 to the power of 3. So here 3 is represented as a exponent number, and this 10 is represented as a base number, and this 3.45 is represented as a mantissa number. That same in a decimal fraction, if we represent a 173.75 number in this format as this 173, this 3 means units, tens, and this will be 100. If we go right side, it will take it as a minus number, that is 10 to the minus 1 and 10 to the minus 2, we had to multiply it. If we shift this point to the left side, we had to multiply it by a 10 to the power of 0, 1 or a 2, depending on the shifting of points or a digit. In terms of binary fraction, it will be if we take this number as same here, if we shift from a left side, then we had to multiply 2 to the power of 0. If we shift this point one digit after a left, then we have to multiply 2 to the power of 0. If we shift right side, then we have to multiply 2 to the power of minus 1. But the problem is we don't actually have a decimal point in a binary. So for example, take it that 250.03125 has a one example. First, we have to convert the integer part of the mantissa into binary number. That is, first we have to take this 250 number to convert. After converting this decimal number to a binary, we will get this number, that is 5101 and 0. Now we have to convert this after point, whatever we have, that point we are going to convert to the binary. That is, if we have this number, multiply and use any remainder over a 1 as a carry forward until continue this until you reach a 1 with no carry. So we have this 0.03125 here. We have to multiply it by 2. So after multiplying, we will get a values of 0.0625. Again, this number we have to multiply and then we will get a value this. We have to continue until we get the values of 1. Here we are after multiplying, we are getting a values as 0. Once we get a values of 1, this will be the ending point. So we have to read the values as an answer as 0, 0, 0, 0 and a 1. This is the binary number after converting this number. Then we have a values as this. Starting this, we have a question that is 250.03125. So, but we need here we have a point, but we have to shift this point to this side because we don't require any point in between this. So, after left side we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 digit we have. So this point we have to shift left side by 8 digit. So this is the same number here, and we are shifting this point to 8 digit. So this is the answer. So shifting of this to a left side 8 times we have shifted. That's why its exponent value is 8. Yeah, that is 1,000. So in that, this is the Mantessa value, that is point. After that, this is Mantessa value. Shifting of point, that is how many times it's 8. So this is an exponent value. So that all we are expressed here. Mantessa value, that is this, and exponent value is 8, and a sign bit, that is starting number is a sign is a positive number. Positive means we have to take as a 0. If it is a negative number, then we have to take it as a plus 1. So that's why we are taking it as a 0. So this is we are doing for a 32 bit. So starting is a positive number, that's why we are keeping it as a 0. And exponent number, that is this number, we are going to keep it as here, and this number we are going to keep it as this. But we require another up to how many bit we required for a 32. So that's why we are using right side as a 0 padding to fulfill the 32 bit numbers. So next is a floating point multiplications. This is the example for a floating point multiplications. Here this is the quotients, that is this is the one number and this is the one number. For floating point, when unpacked the significant are both 1 and a 0, the product is 1, and so the result is of the form 1 up to a 0. To compute the exponent, we have a formula biased exponent of E1 plus E2, which equals to biased exponent of E1 plus biased exponent of E2 minus bias. So first we have to take these values as a here and these values as a here, and
Uh,
then we
One
have
small
to
interruption,
compute.
Musrat. So basically, in a
Yes,
previous representation, whenever you represented a number, you missed out that biasing. So some
yes,
exponent was taken, so 127 plus was to be explained, and the number representations for that three invalid states. One is infinity, or positive infinity, negative infinity, and not a number. The patterns, 8-bit pattern for that, so all ones, all zeros, and whatever the other pattern, those three patterns were to be showcased. whenever you are writing that
Oh,
representations. So make sure that whenever they occur, that should be noted by noting the exponent, not a number plus positive
okay.
infinity, negative infinity, and that exponent is a biased exponent. So it is always 127 plus. Fine.
Okay, sir.
Okay. That you have
Okay.
showcased in multiplication, but not in the representation as such.
Okay.
Okay.
So after they taking the complement of this is the number of this in the form of binary number, and adding this number, we will get a multiplication value here. Since this is a 134 decimal, we have a formula as 134 minus biased. So this is a 134 here, minus biased value is 127. So by the 134 minus 127, we will get the values as a 7 here. Thank you, sir.
Okay, thank you. So one more point. So my name, I am not doctorate yet. I am just Mr. Sunil Matar. Make a corrections.
Okay,
So, okay.
okay.
Okay. Who wants to go next?
Thank you, sir.
Sir, I'll give sir.
Yes, yes. Go on.
Mustaf. Sir, my screen is visible, sir. Am I audible, sir?
Yes, sir. You are audible as well as your slides are visible.
Thank you, sir. Respected sir and my dear friends, I'm Veeresh, third semester, MTech Digital Electronics. Now I'm going to give a seminar on speeding of integer multiplication and division and policies and pitfalls. The contents we are going to discuss in this seminar: speeding of integer multiplication and the addition with shifting over zeros, speeding up multiplication with a single adder, and faster multiplication with the many adders, faster division with one adder, and the fallacies and the pitfalls. So we are seeing the many methods for the in the previously as our friends are explained the methods for the integer multiplication and the division. So with the existing to those methods, how you can boost the speed of the multiplication and the division with some advanced techniques. So that we are going to discuss. The first, shifting over the zeros. Shifting over the zeros, first we'll consider the multiplication operation. As our friend explained, so this is a multiplication operand. So in this multiplication operand, so there are two operands. So that is the A and B. It is placed in the register called A and B. A and B. The multiplication steps, how it will be takes place here in this case is nothing but a so, so it will be considered the last LSB bit of the this A. If it is equal to 1, it will be adds the B plus, it will be adds the B plus with the P and stores the result in the P. If it is the last LSB of the remainder is equal to 1. If it is 0, then it's not doing the operation. It's simply doing the 0 plus P and adding result will be stored back in the P. But in this case, in the shifting over the zeros, so we are avoiding this operation. We are avoiding this operation when the lower order bit of the zero, if the lower order bit of the A register is equal to the zero, so thus we can improve the performance. So we are avoided there the addition operation, one addition operation, so that we can avoid the means we can improve the speed of the multiplication. So that's what the idea behind the shifting over the zeros is, to add logic that detects when lower order bit of A register is zero. So if so, if it is equal to 1, that is the lower order register of A is equal to 1, it skips the addition step and proceeds directly to the shift step. So it will be directly to the next step, that is called as the shift step. So hence the term shifting over the zeros. So its operation, it is the the execution time is depends upon the operand dependent. Here the operand dependent is nothing but here it will be depends upon the register called A. So this is the shifting over the zeros for the multiplication. Shifting over the zeros for the division. As my friend explained, so there are two methods for the division. One will be the restoring method and another one will be the non-restoring method. In the restoring method, first P and A will be P and A will be shifted left. Then P minus B will be done. That is the subtract operation P minus B. So this is the P and the B subtracted operation, and it will be stored back in the P. So then in the fourth in then after adding this one, so it will checks for the whether the result is negative or not. If it is the result is negative, then A will be loaded with A will be loaded with the zero, and if it is not negative, then A will be loaded with the one. If it is negative, then the restore the old value of P by adding the content of register B back into the P. If it is a so that is the means the results of P minus B. If it is a negative, then restore the old value of P by adding the content of register B. This is called as a restoring operation. So then in the non-restoring operation, it will be operation will be done with the by checking the whether the P is negative or the positive. If the P is negative, first it will be first if it will be checks the whether the P is negative. If the P is negative, then shift the P comma A by one bit left, then add the B plus P and stores the result in the P. Else it means P when this is the P is equal to negative. When P is positive, during that time shift the one bit left and P minus B. P minus B, so that the subtraction operation will be done and store the result back into the P. And checking the condition whether the P is negative or the positive. If it is negative, then A will be loaded with the zero. So that is the loaded with the higher order. So that is the loaded with the zero. And if it is if it is a positive, A will be loaded with the one. So here, so A consist at the end. A will be consist of the quotient and B will be the remainder. If this reminder, this is the P is a non-negative, that is the reminder is non-negative, then it is the reminder. If it is a again, if it is a what if it is a negative number, then we have to restore the values back. So that is the what the non-restoring algorithm. So this is what. To speed up shifting over the zeros cannot be applied directly for the non-restoring division. An ALU operation is performed at every step. No opportunity for skipping the no operation because checking the values of checking the sign of the P, that is the reminder, that is the P product register, checking the sign and doing the arithmetic operation. It is the addition or the subtraction. So think the division in this way. First, to compute the A comma B, subtract the multiples of B from the A and then report the how many subtractions you have done. So that is the first. Then second, at each stage, subtract the remainder must be fit into the P register. So here compute A comma B, subtract the multiples of B from the A, then report how many subtractions were done. So then subtract the remainder must fit into. So subtract the result will be get into the P. Then the remainder is small. When the remainder is small positive number, during that time first shift the remainder, then subtracted the B the next time. So instead of directly subtracting the what B with the P, first when the remainder is very small, first it should be get shifted, then subtract with the B. This is the idea called SRT division. So this is the SRT division. So the SRT, the name of the scientist it is. So this is called Spinney, Robertson, and Tuffer. So this is the SRT division. This is the idea for the SRT division. So now we'll understand the shifting over the zeros for the SRT division algorithm. So SRT division algorithm, it is similar to the non-restoring algorithm. It is a slightly different with that. I mean similar to that, but with a slight difference. Okay, to divide A by B, where A and B are the n bit numbers. and load A and B into the A and B registers respectively. The two numbers load those two numbers into the registers called A and B. So SRT division algorithm, if B has a k leading zeros at the most significant bits of the B as a k leading zeros, when expressed using the n bits, shift all the registers left by k bits. So first algorithm in this case, if B has a k leading zeros, means like when expressed using n bit, shift all the registers by the k bits. For I is equal to 0, n minus 1. So this is the length of the each register. That is the length of the each register. If the top three bits of the P. So in the top three bits of the P, that is the product register, is equal. Set Qi will be equal to 0. Here quotient will be determined here based upon the reminder. So here a reminder is the P, and with the help of the P, you are going to determine the quotient value. If the top three bits of the P are equal, set Qi will be equal to 0, and shift P comma A one bit left, one bit left, then one bit left, and add the B. So that is the one bit left. So when these are the three, if the top three bits P are not equal, then P is negative. So then the P is negative. Set the Qi will be equal to the minus 1, and shift P comma A one bit left and add the B. Otherwise, set Qi will be equal to 1. Shift P comma A one bit left to the and subtract the B. So here here. This is the algorithm. This algorithm is what goods for the two radix division operation. In the two radix method, so we are having the set means we are having the values. So minus 1, 1, and the zeros. If the final remainder is negative, correct the remainder by adding the B, and correct the quotient by subtracting the 1 from the Q naught. Finally, the remainder must be shifted k bits. So in the initial it has been shifted to the what it has been shifted to the right. So now again it will be again shifted back. That is the k. The final remainder must be shifted k bits right, where k is initial shift. The SRT division of 8 by 3. So we'll understand this with the this algorithm by taking an example. Here is an example. So this is the 8 by 3. So this is the A register, and this is the product register called P. So here B contains, so in the initially B is the 0011. So here in the step 1, B had two leading zeros. So here observe it over here, it is having a two leading zeros. Those many times you have to shift the B and A, means like B and P comma A registers. So now after shifting B, after shifting B, we contains 1100. So it has been left shift. It has been uh, yes, it has been left shifted by 2. So after that, so it will be contains the 1100. Then so it is also been shifted here, because P comma A, this is the together register. We are taking, so 00, so two times it has been, that's why it is over here. So 0010 and four zeros. In the step 2.1, top three bits are equal. Checking the condition here, top three bits are equal. Yes, it is equal. So this is the case A. So in the case A, so we have seen that if the top three bits of P are equal, set Qi will be equal to 0, and the shift the P comma A one bit left. P comma A one bit left. So that's what setting the Q naught, that is the quotient bit will be equal to 1, and the shift. So that's why here it is the quotient bit which will be get added, and the shift one bit left shift. That's why one it is been come over here. Again step 2.2, checking the condition. Top three bits are equal condition it is checking. No, it's not equal. So P is greater than, P is positive in these cases. So that's why I said Q1 will be equal to 1, and again shift. So that's why Q1 here, that is the Q1 here, that the quotient bit here it will be set equal to 1, and it will be left shifted by one time. Then subtract. So in this case subtract the B here. So this is the B value here, it is there, that is the shifted value with the 2's complement number. So we are subtracting over here. This is the final result, triple one double zero, triple one, this is the triple one and 1. So this is the sign bit last. Then again checking the condition, step 2.3, top bits are equal. So stop bits are equal. Yes, it is equal. Then Q2 will be equal to 0, and shift. So q2 will be equal to 0. So again adding the quotient value to the what the register a, so that is the 0. Then shifting the what one bit, then shifting the one bit, then again checking the condition. So this is the final this one. So then checking the condition, top three bits are equal, top three bits are equal. If it is so, no, is the case top three bits are equal, no it's not, it's not equal. So then and in this case set q3 will be equal to -1. So here set q3 will be equal to 1 is nothing but a what. So here here the p is negative, that's why we are setting the q3 will be equal to 1. So during that time, so you are adding the b, so adding the b, so that's why you are adding the b value. So b value is 1100 to the this value you are adding. So here this is the quotient bit you are adding, that is called as a -1. This is the quotient bit, so final value will be over here. So again, reminder is non-negative. So here there are means like 0 to n minus 1. So there are four bits are there. So there are four operations are over. So this is the final value 11100. Reminder is non reminder is negative. Here checking the in the third step, reminder is the negative number here, whatever you have been taken, so that it is checking for the negative, whether it is a negative or the positive. So obviously it is a, in this case it is a negative number. So restore it back. So how we can restore it? So we can restore it by adding so reminder by adding the b, and quotient by subtracting 1 from the q naught. So after subtracting the 1 from the q naught, so adding over here and adding over here, so we'll get the 01000. So must undo the shift step by 1, right shift by 2 to get the reminder. So reminder is 10 here.
हाँ सर
This is the reminder is 10. The quotient is, this is the quotient.
ಏನು
So this is the 0101
ಹಾಂ ನೋಡು
minus 1.
ನೋಡು
So this is the value of
ಮಾರ್ಕ್ಸ್ ಆಗ್ತದೆ
0010. So this is the 8 by 3. If we divide it over there, so that is the quotient value will be the 2, and the
ಎಸ್
remainder value is equal to the 2. So this is how the
ಆಯ್ತು
SRT division will be applied.
ಹಾಂ ಆಯಿತು
Operation will be takes place. So this is the, it will be
ಆ
estimate
ಪಿ
the
ಜಿದ್ದು ಹಾಗೆ ಕಾಪಿ
what
ಮಾಡಿರಿ
it
ಮಾಡಿದ್ರೆ
will be estimate
ಆಯಿತು
the
ಓಕೆ
quotient values based upon
ಹಾಂ
the b values. So based upon the b values, and also not b values, based
ಆಯ್ತು
upon
ಇದು
the
ಇದೆಲ್ಲ ತಿದ್ದು ಕಳಿಸ್ಲೇನ್ರಿ ಮತ್ತೊಂದು
so
ಮಾಡಲೆ
here the difference between the SRT division and ordinary non-restoring division. The difference. So as I
ಅಲ್ಲ
told, so
ಸೈನ್
both
ಮಾಡ್ಯಾರಲ್ಲ
are
ಅದಕ್ಕೆ
similar with a slight change. What is that difference? So ALU decision tool.
ಅದೇ
So in non-restoring division, it is determined by the sign of the p. In non-restoring, by seeing the sign whether the p is negative or the positive, because by seeing that, so addition or the subtraction operation will be takes place. But in SRT, it is determined by the two most significant bits of the p. That is the most significant, like whether we consider the higher arguments, those are equal or not. Like most significant bits, that is the remainder bits of the p. Then final quotient. In non-restoring the immediate value will be available after the each step, but in the SRT three quotient digits 101, so it is been available, so it is been available in the form of 101. So for this one, so you do require some additional adder to add the multi to add these means to convert these into the adder and to give the final result. Then speed. SRT division will be faster, no operands that produce the zero quotient bits here, due to which so speed of this SRT will be more. Then so here discuss, so that is the shifting over what zeros. So although this is the technique of shifting over zeros is not currently used much, it is instructive to consider, and it is distinguished by the fact that the
ಸೆಮಿನಾರ್
register
ಓಪನ್
time
ಮಾಡಿತ್ತು
is operand dependent. So next
ಇನ್ನೊಂದು
one
5
is
ನಿಮಿಷ
speeding of
ಆಯ್ತು
multiplication with the
ಹಾಂ
single adder. So yeah, here so multiplication with the single
ಬರ್ತೀನಿ
adder.
ಒಂದು 5 ನಿಮಿಷ
So here we have
ಮುಗಿಸ್ತೀನಿ
been discussing it here. This is the add. So in the multiplication, so this is the part. This is the main part. This is the adder. So this adder with some advanced technique, we can speed the operations of the multiplication. So how we can with the advanced techniques of the what adders we can be boost the performance of the mm, multiplication, we'll see here. So speed of the multiplication with a single adder. So here it has been employed, the first one it is being employed the carry save adder, as my friend explained. So it is associated with the, there are three inputs and the three output, and also each of this carry save adders. So each of the means it is having n independent full adders. All the means full adders, that the carry save adders will be work independently. It will be not depends upon the any carry. and also carry will not be get propagated. So this is how, so this is the carry save error is simply collection of n bit full adder. So each circle is marked as a plus, is a single bit adder, and each box, so here each box is represents the one bit of the register. Here there are 6 bits, and also here also 6 bits is there. So this is the plus, this is the plus for the indication of the carry save adder. So these are all the these are the box are for the 1 bits representation. So here is a carry, so these are all the means these carry save adder will be like this is the carry save adder will be simultaneously, means like parallelly it is calculating the calculating the results, and it will calculating the results and updating the p will be consist of the two register, one for the sum bits and another for the carry bits. So after every add operation, the sum bits will be right shifted to the a operation to get the multiply value. To operate the multiplier in the above figure, load the sum and carry bits of the P with a 0 and perform the first ALU operation. Then the shift the lower order bits, lower order sum bits of the P into the A, as well as shifting the A itself. Then speeding of the multiplication with using an extra adders. So extra adders with the using the extra adder, we can speed up the multiplication. So here only we are checking the condition. It is examining the k low order bits of the A at each step. So register A is there. In the register A, lower order bits it's checking whether to perform the means like what multiplication operation or not. So are the subtraction operation or what addition operation to be performed or not. So here suppose that k is equal to 2. So so if the pair of the bits of the lower order bits of the A is equal to 0 0, then add 0 to the P. So then 0 1 add B to the P. Then 1 0 simply left simply shift one bit left before padding it to the P. Then unfortunately, if there is a 1, it appears to be a B plus 2B. So B plus 2B. So with the help with the of this mm, with this extra adder, so with the by means determining by predicting the this lower order bits whether the 0 0 1 0, we can reduce the performance of the multiplication. So this is the higher radix multiplication. So then booth recording. So in the booth recording, it can be overcome the when it is a 1 1 with a b plus 2b in the recording algorithm. So in the booth recording algorithm, this is also called as a overlapping triplets. So overlapping triplet, it means that so it will be use the three bits to determine the multiple value for the p, multiple value for the or the addition value for the of the b. So here lower order bits of a, that is the 2i plus 1, then the 2i is there, then last bit shifted out, that is the 2i minus 1, then the multiple. If the 0 0 are there, then the last bit shifted is also 0, then the multiple of the b is equal to the 0. So then 0 0 and last bit shifted is equal to 1, then plus b added. So like that it will be there. So this is the multiples of B to use the for the radix for booth recording. So we can see it over here. So this is the P and A, and this is the L. This is the last bit shifted out. Multiply minus 7 times by minus 5. So this is the unsigned number 7 and 5. 7 divided by 5. In the initially the B contains the 1 0 1 1. So B, this is the 5, that is minus 5, that is the B contains the 1 0 1 1. So lower order bits A are 0. So here lower order bits A are 0. So 0 and 1. So here both are the 0 and 1. And the last shifted bit here in this case it is equal to 0. So add B. So just simple add B. Like that the operation will be get performed. The product will be, this is the product value. Final value it will be appears over here, that is the 35 over here. This is how the booth loading by determining the means early of the how much the b to be get added, whether it is a 0, whether it is a b, or whether it is a 2b, how much it should be getting added to the what with the what P will be boost the performance of the multiplication. So then faster multiplication with the many adders. So you see, till now we have been discussing with the faster multiplication with a single adder. There we have used the only carry save adder. But here, with the help of the multiple adders like carry save adders, propagate adders like ripple carry adder, carry loop adder, carry skip adder, like that. Use of multiple adders using boosting the performance of the faster multiplication. See here, so there is a carry save adder, carry save adder, and carry save adder, and so there are carry propagate adder. So here in this one, so carry save adder, so for the in this case, so there is a 5 bit number in a is multiplied 5-bit number A is multiplied by B4, B3, B2, B1, and the B0. So this is the 5-bit number. It is been multiplied with the A. So this is how it will be. The operation will be takes place over here. So first 3 bits, because carries CSA, that is the carry save order, 3 input and 2 outputs will be there. So same. So here it is been the structure. Structure it has been shown
చెప్పండి.
near the end. There is a
చేస్తాను.
carry propagate adder will be used to accommodate to calculate the sum of the all the means all the final
ಸರ್
result. So here in the B, it has been shown how the
ಹಾಂ
operations
ಮಾಡಿ
to
ಸರ್.
first in the CSA, in
ಹಾಂ
the
ಹಾಂ
CSA how it will be do, what is the values it has been doing. So B naught into A. So this is the B naught into A naught, and the B naught into A1. The next one, the B naught into A2, then B naught into A3, B naught into A4, like that. So this is the how
ఆ
it
క్లాస్
has
నడవదు సార్.
shown the input to the array. So this is how the internal structure of the for this one. So internal structure of for this one is the so adders. So in the CSA, so how many adders it will be get users. So those all the things in full detail it is been displayed over here. So here, simple array multiplier for multiplying the two 5-bit numbers using the three CSAs, using the three CS and one propagate adder. Array multiplier performs same number of addition. So here also same number of addition as compared to the CSA. There is no much improvement. Latency is not dramatically different. But hardware of array multiplier this can be pipelined so that throughput can be increased. See here, so this is the CSA is there. So this can be pipeline and using the parallel, so we can be improve the operation or speed of the operation by doing parallelly compared to using the CSA, that is the with the single adder. Then faster multiplication with the many adders. So in the faster multiplication with the many adder, so here it is a multi-pass array multiplier, considering the multi-pass array multiplier. So in this case, we consider the two-pass array multiplier. So in the two-pass array multiplier, first p of the bits that will be passed and the result will be calculated. Then next time again another bits will be means remaining bits will be passed to calculate the final result. So sometimes space is budgeted on a chip for its arithmetic may not hold an array large enough to multiply two double precision numbers. First
ఎత్తలేరు.
pass through the array retires 5 bits of B. Returns 5 bits of B. So here, so B naught, B1, B2, B3, and B4. First 5 bits it will be get passed. So this is the 8-bit multiplier. First 5 bits it will be get passed
హలో.
pass. So it is fed back into the again after the result of first pass is then again fed back into the top to be get combined with the next three summands. It will be get combined with the next three summands. Here we are considered this is the B5 of A, B6 of A, B7 of A. So with these summands it will be get
ಸರ್ ನೀವು
use
ಹೋಗಿರಿ
of
ಇನ್ನು
the
ಲೇಟ್ ಆಕತ್ತ
results
ಅಂದ್ರೆ
it
ಸರ್
will be get
ಮೋಸ್ಟ್ಲಿ
added
ಇನ್ನೊಂದು
with
15
that.
ನಿಮಿಷ ಹೊಡಿಬೋದು.
Okay, so added the
ಎಲ್ಲ
result of
ಮುಗಿಸೋಲ್ಲ
this
ಇನ್ನೂ
reading
ಹಂಗೆ
pass is
ಹೊಡ್ಯಾತನ.
then fed back into the
ಓಕೆ.
CPA. This is the
ಹಾಂ
carry propagation
ಹಾಂ
adder,
ಅದು
and
ಆಯ್ತು
here
ನೋಡ್ತೀನಿ.
hardware is less, and
ನೋಡಿರಿ
the
ಆದ್ರೆ
pipeline
ಬರ್ತೀನಿ,
is
ಇಲ್ಲಾಂದ್ರೆ
not
ಮತ್ತೊಂದು
possible
ಹೋಗ್ಬಿಡಿ.
as it will be involves
ಎಸ್
the
ಸರ್.
feedback. But
ಪಿ ಜಿ
with
ಪಿ ಜಿ. ಹ್ಞೂ.
some techniques, so we can increase the pipeline
ಒಬ್ಬ ಹೊಡ್ದಾನ ತಡ್ರಿ ಪಾಪ ಲಾಸ್ಟಿಗೆ
some
ಎಲ್ಲರದ್ದು ಆಗೈತೆ
condition
ಒಂದೇ
to
ಹಾಕಿದ್ವಿ.
improve the performances. So faster multiplication
ಎಸ್ ಎಸ್
with
ಸರ್.
many
ಹ್ಞೂ.
adders,
ಓಕೆ
even
ಓಕೆ.
and odd array. So in the even and odd array, so like operations of the sum bits will be divided, and it will be doing over here. So here the idea of the design is that two adds proceed in the parallelly. So divide the operation to be number of bits over here and number of bits. So divided that and parallelly doing that. So it will be improves the performance and the speed of the operation. And fast multiplication with the many adders, that is the values tree multiplier. So in the values tree multiplier, so here that is a tree like structure kind of the add it will be used to boost the performance of the what the multiplication. So in this case the In these cases, summons of b0 a and b up to the bn minus 1 into a, cutting the number of summons into the, yeah, first cutting the number of sum into the n by n into the n by 2, then n by 2 into the n by 4, then and so on so on. So this is, it will be get continuous. So in this case, the idea does not map to the full of 3 comma 3 full 3 comma 2 adder. So 2 adder which reduces the 3 inputs to rather than reducing the 2 inputs at one tree. So this is the values tree. Then fast multiplication with the many adders, that is the signed digit tree. So here signed digit table. So with the help of signed digit table, signed digit tree representations are minus one, minus one, minus one, and the zero. This representation as a two cache. First, it takes the two bits to represent each signed digit, and second, the algorithm for adding the two signed digit number is a and b, and is complex and requires examining the ai and a minus one, and compute the si plus ci, and then defines the 2 comma 1 adder. With this hand, we can use the straightforward binary tree to form the multiplication. And in the step of a, in the step it adds the b0a and b1a in the parallel manner, and thus the next step adds the result of these sums in the pairs, and so on. Although the final sum must be run through the carry propagate adder to convert it from the signed digit form to the choose complement. This is the final step which is necessary in any multiplication, any multiplier, which using the CSS. Using the CSS, at the end there should be a propagation, carry propagation adder to find the sum of the value. So then faster division with one adder. So faster division with one adder. So we have discussed the SRT division algorithm. The same thing it's been employed it here also. So with the one adder, so it may be a one adder, it may be a CSA, or it may be a carry CPA, carry propagate adder. So here, so in the faster division with one adder, so with the help of the radix 2, the quotient in when we are considering the radix 2, the quotients selections will quotient selections are, so minus 1 1 and the zeros will there. So in the radix 2, so this is the method, this method can be improved with the help of the SRT division operation. So in the carry save division, the idea is that because the reminder and is not known exactly, the exact quotient digit is also not known, but the redundant representation of the SRT, the reminder does not have to know the precisely in order to pick a quotient digit. So here, a reminder does not need to know the precisely in order to pick the quotient digit. So here in the above figure, so we are going to define the range for the quotient. What is the range for the quotient for the b values? So here, so this is the so where x-axis represents the Ri, that is the reminder values, and the reminder for after I steps, reminder for after I step, the line labeled qi will be equal to 1. So line labeled qi will be equal to 1 shows the values that Ri plus 1 would be if we choose the qi will be equal to 1, and similarly for the lines qi will be equal to 0 and qi will be equal to minus 1. So here, so this is the Ri, so there it is being defined it, this is the reminder value. Then when the qi will be equal to 0, so this is the qi will be equal to 0, qi will be equal to 1, so this is the qi. So that is the next one, that the ri of r of I plus 1, that is the next reminder it is there. That next reminder can be get calculated with the 2 ri minus qj into b. So that is the next reminder we are calculating over here. So then it is here it is been for the range for the what for the range for the quotient to be determined based on the reminder is in this manner. So for the q j is equal to 0, so it can be like b by 2 and plus plus or minus d by 2 with a bounded value, so minus plus or minus d by 2, and qj will be equal to 1, so it is a 0 to b, so that is the qj will be equal to 1, you can choose it for the remainder. So in the case, so as I said, based upon the remainder, so you are choosing the values of the quotient for the yeah, division operation, so based on this, so okay. Mm. So as I already explained the SR2 to radix division operation. So first division with one added, and again it will be get continued. The quotient selection for the radix 4 division with the quotients. So in the radix 2, the quotients are minus 1, 1 and the 0. In radix 4, minus 2, minus 1, 0 and the 1. In the what in the radix 4, it uses the lookup table to find the what the division operation. So the design challenge when building a high-speed SRT divider is figuring out how many bits of P and B need to be examined. So for example, so here we are consider the radix 4. This is uses the quotient. For the ordinary radix 2 non-restoring division, the it will be less than the that remainder will be less than or equal to B. But in these cases, so we have to consider that Ri plus 1 will be equal to the 4 Ri minus Q of I and B, as we consider for the radix 2 operation. So in these cases, remainder might grow with the means whenever you are choosing the what the value of the value for the quotient, a remainder should not go without bound. You know, should not go without bound. Out, it should not go out of bound. It should be within the bound such that it will be leads to the exact result. So in these cases, restricting the Ri with the help of which is less than the 2 by 3 makes it easy to check for the Ri will be stay bound. So in these cases, so you can observe it. You can observe it over here for the 0. So the multiples of b you can be choose it, the b you can be choose it. So this is the Ri remainder value for the corresponding to the this remainder value. You are choosing the quotient values over here. So for the zero quotient, the values of the b will be the minus b by 6 to the plus b by 6. So then for the 1, b by 12 to the 5 b by 12. For the 2, b by 3 to the 2b divided by 3. For the minus 1, minus b by 12 to the minus 5 by 12. And minus for the minus 2, minus b by 3 to the 5b by 3. These are the bounded values. So these are the bounded values. See here, this is the lookup table. It is been formed with the previous one, how we have been considered. So here example, so there is a b value is will be equal to, here in this case it is a 8 is there, 8 is there, and so in the 8, sir.
No, nothing as such. You just finish this slide and we'll wind up. So remaining part can be for self study.
Oh, okay, sir.
Okay.
Okay, sir. Okay, thank you, sir.
Okay.
So quotient digits for radix for SRT division. So in this case, 8 will be get considered top rows of if the higher order bits of 4 bits of B. So here 4 bits of B. So in this case, so that is the it will be equal to the 8. And if the top bits 6 bits of the P are, so minus 12 and minus 7. If the P, so that is the remainder bits are minus 12 and minus 7 is there, so then you are going to choose the minus 2 as the quotient value. Why you are choosing the minus 2 as the quotient value? Because there it is a b is equal to 8 is there. So that b is equal to 8. So it will be false in the range of, if you choose that, it falls in the range of b by minus b by 3 to the b. So that is how you can be prepared the remaining values for the what the lookup table, the this kind of the method. So this is one example. You see for the this is the radix, so four division operation, it's same as that of the radix 2 SRT division, but here we are considering the six to 6 bits we are checking. We are checking the this on the P register up to 6 bits we are checking and following the condition. So these are the some pitfalls and policies and the pitfalls.
Let the say fallacies and even self study between it. So that's
Oh, okay.
more than sufficient for seminars as such. Okay. Thank you, Varish, and thank you, everybody. Okay.
Thank you, sir.
Okay.
Thank you so much.
So
Thank you, sir.
please share your slides onto the classroom so that you exchange it in that platform message. So
Okay.
assignment, submit over the link. And third IA, as I stated, with respect to VLIW architecture and scientific computing, large scale scientific computing. Okay.
So only that computer arithmetic is not there, sir.
Computer arithmetic is not there. So computer arithmetic is for your. I just wanted to finish the syllabus officially. That's where computer arithmetic is there. But for IA, only two chapters:
Okay, sir.
VLIW and this last scientific computing. Say that appendix.
Okay, sir. Okay, sir.
Okay. Okay.
Thank you, sir.
Thank
Thank
you.
you so
Thank
much.
you.
Yes.